All right. Hi, everybody. Thanks for coming. Everyone excited to be here for October? Yeah, it's October. Yes. All right, well, good to have everyone here. We're at our new host this month, NYU. So everyone, round of applause for NYU. Thank you for hosting us. One of the conditions we had for being here is that we insisted the NYU person speak to put him on the line. So she's actually filling. We had a bit of a schedule shift from last month. We had to move forward a speaker, and we had to move forward another speaker. So he should have been speaking in November, which is why he's just finishing up his slides now. So thank you very much for filling in for us and for arranging this beautiful space. So first up, we always ask at this meetup, is anyone hiring? Who's hiring? Fewer people post-pandemic are hiring. All right, so if no one is hiring in the room, people who are here virtually, if you're hiring, go to the nyhackr Slack. You can find it by going to nyhackr.org and clicking the little hashtag at the top, and you'll be able to go find the Slack and go to the job postings channel and let people know about the job you have. Great. Since no one is hiring, no one wants to give someone a job, let me go to my other announcements. They are, all right, the pizza. The pizza this month came from Ben's of Soho. So let us know what you think. Go to bit.ly/pizzapoll. That's bit.ly/pizzapoll and rate the pizza. It's a scale essentially from 1 to 5. They're categorical, but it's an ordered scale. Let us know how the pizza is. For those of you that have not been here before, you know that we don't know that we've been collecting these data for 12 years or something, at least 10 years. No, definitely more than 10 years. So we want to keep that going. So if you're in the room and you ate pizza, go to bit.ly, pull out your phones. I see everyone just sitting there staring. Pull out your phones, go to the website, and vote the pizza. I see Paul's already doing it. Thank you, Paul. Everyone should vote on the pizza. Let us know what you think. Those of you that are attending virtually, hopefully you have pizza wherever you are. But if you didn't have pizza, hopefully you had some good food or snack or beverage that you enjoy. Let us know in the chat. Speaking of chat, there are 2 ways you can chat with us, and this goes to people in the room too. Go to the nyhackr. There's a channel called Monthly Meetup Chat. Or go on the YouTube live stream and chat right in there. Let us know where you're eating, what you're eating. If you're eating anything at all, if you're not, let us know what you're imbibing, or just let us know you're live. So everyone in the room, hope you enjoy the pizza. Next week, we have our annual R in Government conference. There's a 2-day conference plus a day of workshops held down at Georgetown University in Washington, D.C. It's about R and friends, because it's an open conference. Just like our meetup group, we have R, Python, Julia, SQL, Go, anything about data, anything that's open. It's a conference next week. If you want to learn more, you go to rstats.ai. It takes place Wednesday through Friday. If you want a discount code, because you're members of this group, this goes for people in the room and virtual, because it's both in-person and virtual, you could use code nyhackr for a 20% discount at rstats.ai. And we will be giving away to this room. This is the last giveaways we're doing before the conference because it's next week. We're going to give away 1 ticket to someone in this room and 1 ticket to someone attending virtually. And you can redeem those tickets for either a virtual or in-person ticket, depending where you are. So hope people will attend that, have a good time. We've been putting on this conference. I think this is the 6th year now. And it's really good time to learn about the R's use in both. Not just both. R's use in federal, local, state, county, and international governments, and for the public sector at various NGOs. It's going to be a very fun time. Then apparently everything I just had on my list just disappeared. Okay, that's disconcerting. So, oh, here it is. Great. All right. Our next meetup will be back at NYU, not in this room, in a different room, in Pless Hall. Is that nearby?
Yes, it's right there.
Down the street from here, our next meetup will be November 14th. Put that in your calendars. But remember I said we had to shuffle the speakers around? The September speaker canceled. We had to move October to September, November to October. We need a speaker. We have the date. We have the venue. We need a speaker. If no one volunteers by next week, I will volunteer someone. All right? Someone in this room maybe. I will point at you and say you're speaking. All right, that's the way this works sometimes. So November 14th at NYU, but we still need a speaker, so please help us out. If you don't want to speak, find someone who does want to speak. When you came in the back of the room, there's a bunch of hex stickers. Grab some more hex stickers, take them home. Put them on your belongings. Enjoy the hex stickers. For people in the room, we will do Q&A after we do the ticket giveaway. For people not in the room, if you ask questions on either the Slack or on YouTube, I will collate those and ask those questions for you afterwards, okay? So in the room, you can ask questions yourself. Not in the room, we will collate them for you. All right? So with that, hope everyone's having a great time and is ready for our speaker. I want to have a big round of applause for doing this a month early. He was literally finishing the slides a few minutes ago. Everyone, please welcome George.
Thanks so much, everybody, for being here. For those of you who listened to me speak at the New York City Art Conference, this will be a little bit of a refresher, but diving a little bit deeper. And so today I'm going to be talking about BART. It's short for Bayesian Additive Regression trees. It's a powerful machine learning model. It has applications for prediction and also inference problems. And I'm going to be giving some background on what BART is, how does it work, why would you be interested in it, and then spend a lot of time in how do we actually use it. Like if you're a practitioner, if you're out in the world and you want to try to apply this to your work, how do you get started? And so we're going to be taking a broad survey of what you can do with BART, and my goal for today is to try to introduce you guys to some areas where you can explore deeper. So I want to think of an example of the hyper shoe. So a sporting company has just released a new high-performance shoe, and they're going to call it the hyper shoe. And they're going to claim that maybe there's a relationship of some sort between the shoe and how fast you can run a marathon. So let's say, given some data on runners, say we have a bunch of data from a prior year in the Boston Marathon, maybe some runners wear the shoes, some runners don't. We know their qualifying times for the marathon. Can we predict this year's marathon time using that data? And so we have some example. We've got prior race as a predictor. We've got this variable z, which is just denoting, are you wearing the hyper shoe or are you not? And we have our outcome, which is how many minutes did it take you to run the Boston Marathon. Now, if we look at our data, it looks a little nonlinear. Now, there's a bunch of tools we have at our disposal to handle nonlinear cases, and we're going to walk through some of the options that we'd have if we wanted to just make predictions. Right now, we're really not making any inferences. We're just trying to predict the outcome running time. So a good starting point is we could fit a linear regression. Now, I've fit a linear regression on the left side of the screen and the right side of the screen. And our RMSE, our root mean squared error, is about 17 for our training data, and it's also about 17 for our testing data. And so what this means is linear regression is performing about the same on an out-of-sample data set as an in-sample data set. In the machine learning literature, we'd say that it is higher in bias and lower in variance. We say it's higher in bias because our predictions aren't that good. We could probably do a little bit better. An RMSE of 17 seems pretty high. We're not really predicting each runner's time particularly well, but the good news of using this model is our predictions are at least not degrading when we try to predict the future or data we haven't seen. Now, another approach is we could do what's called the regression tree. Now, this is something that people are a little bit less familiar with compared to linear regression, and so I'm going to spend some time on the intuitions behind a regression tree. You can think of regression trees as an extension of analysis of variance, if you're familiar with that model. We've heard of ANOVAs before, and the idea with an ANOVA is we're just trying to see how much variance is explained conditional on some groups. Usually these are categorical variables, so we can calculate the mean, sum of squares within versus sum of squares between for a callback to intro stats. So the idea of a regression tree is we have a continuous variable, and if we could just make one cut in our continuous variable, where do we want to draw the line to explain the most variance in our outcome? And so if we limit our regression tree to just making one cut, the best cut we can make is somewhere between a qualifying time of 250 minutes and a qualifying time of 300 minutes. Now, to the left of that cut, we're just going to take the mean, the average of all the data points. And to the right of the cut, we're just going to take the mean of all the data points. And that's going to be a prediction. Now, we wouldn't expect this to predict very well. We can just visually see that it's not fitting the data particularly good. But we can keep making cuts. We can make multiple cuts and keep growing. So now, it may be a little small. I hope people can see that. So now on the training data set, RMSE is around 20. So we're still doing worse than linear regression. And our test set is around 21. So we're still not making a lot of progress. But now we have kind of 4 groupings of means. We've made more cuts along, in this case, qualifying time, one of our predictors. And we're just taking means within each of these cuts. Now, the thing about regression trees is we don't have to stop. Nothing's stopping us from making more and more and more and more cuts. And the more and more and more cuts we make, the better we're going to get at predicting our in-sample data. Now, sometimes this can lead to making better predictions out of sample, but there's going to be a point where maybe things start turning around. So if we make more and more and more cuts, our in-sample predictions for RMSE now go down to 12. So now we're outperforming linear regression. So it's pretty easy to model this data better when we don't assume a linear pattern. And as we can see, the data is not particularly linear, so this shouldn't be surprising. Now in this case, our test set starts jumping up a little bit more. As we saw earlier, the kind of gap between training and test was pretty small. Now it's starting to get a little bit larger. So in the machine learning world, this would be what's called the bias variance trade-off. So we can start modeling the data we see much, much, much better, but at some point we're going to start overfitting that data, and we're going to start chasing noise. We're just going to start chasing patterns that actually aren't there, and that's not going to help us make predictions for data we haven't seen. And most of the time in sports analytics or business or science, we're not interested in just the data we have, but also the data we haven't seen yet. And so that's not going to help us. Now, in this example, it's still not bad. A 13 RMSE, we can live with that. It's only a small jump. We went from kind of an RMSE of 12 in sample to an RMSE of 13 out of sample. So that's a still not too bad, but what if we kept going? Now we could imagine we go and go and go and go till we basically cut for every single data point. And our prediction is our observation. Now that's going to be really problematic for us. So we need some type of strategy to keep getting more and more flexible, to keep kind of fitting the data more and more nonlinearly, but also guarding against overfitting. And by overfitting, this kind of gap between our ability to predict on the data we actually have and data that our model hasn't seen yet. Now, one of the most popular tools for this challenge it's called gradient boosted regression trees. So gradient boosted regression trees take the idea of a single regression tree and build a bunch of them together. So what if we have a bunch of really, really small regression trees? So the idea is, well, if just one tiny tree boosts another tree and then that boosts another tree, we can get really flexible nonlinear predictions, but still guarding against overfitting. Now, how do we actually keep the trees small? In the examples I just walked through, you saw that I could control how many cuts we're making. Now those are all tunable parameters in these algorithms. The question is, what do we set them to? Well, usually we rely on things like cross-validation, where we just try a bunch of options out and see which ones work the best. Usually you hold some chunk of your data out, you fit your model on the data you've decided to keep, and then see how it'll perform on the subset that you've held out. This is very, very common. I'm sure it's not surprising to a lot of people in those rooms, in this room. And so if we add together each of these small regression trees, our predictions are going to be more flexible, and we're keeping them small by kind of keeping the amount of cuts limited. And we're picking that limit through cross-validation. There's also other important parameters called a learning rate. It's just a small number we're going to multiply to each of the predictions to kind of shrink it a little bit. Again, it's a tunable parameter. In the case of gradient-boosted trees, these are the two most important parameters that tend to be focused on during cross-validation. Okay, so this is all very abstract. Let's think about what's actually going on. So the first step of a gradient-boosted regression tree is we're just going to start with the mean. If we don't have any other prediction, just the average of our outcome-wise, probably the best we can do. So we're just going to start there. And then we're going to fit a really small regression tree. And we're going to take the residual from the mean, and we're going to fit the regression tree on that. So we have our prediction the mean. We basically say, well, how far away is each data point from the mean? And we're going to fit a regression tree on that. And we're going to keep that regression tree really small. And then we're going to take the residuals between that mini regression tree and the remaining data. And we're going to fit a regression tree on that. And every step we're kind of multiplying by the shrinkage parameter. And it's keeping the trees from learning too fast. Now, if we didn't have this shrinkage parameter, what would actually happen is after like 2 or 3 trees, we'd be overfitting again, and it's going to really prevent us from moving too fast. And really slowly, we're going to get more and more and more flexible. And we're going to keep growing slowly and slowly and slowly. And each step, we're getting a little bit smoother, a little bit smoother. This is after 10 trees. And usually, we have a lot of these really small trees. When I say a lot, it's not just 1 or 2. Usually, it's in the hundreds, like 100, 125. Those are some good ballpark estimates. Sometimes we'll go down to 75, depending on how your data is structured. And we could keep fitting and fitting and fitting, and ultimately we'll have some final model we'll use. Now, interestingly enough, the R code to produce these models is actually pretty not too complex. You can do it in about 10 lines. If you ever want to fit your own gradient boosted tree. But if we fit it to our running data, we see now that we're modeling things much more flexibly. So in the in sample, we're still at 11, and in the out of sample, we're at 12.8. So we're doing better than we were with some of the regression trees and the linear regression from earlier, but we're managing the overfitting a little bit more effectively. And we can see our model on these data points is hugging the data much, much tighter than our regression tree was. So now we're modeling things much more flexibly without trying to just make a cut for each data point and predict yourself. Because it's not going to help us. It's not going to do well when we're interested in things that we haven't seen yet. Now the question today is, can we do better than this? Is there something else we can do? And some of the challenges with this approach is, well, we have to do a lot of cross-validation. And cross-validation takes a lot of time, especially on big data sets. You could, in theory, expand the grid forever. Now, there's some optimization techniques you can use to try to make better guesses, but at the end of the day, you're going to have to do a lot of cross-validation. And also, we're just left with a single prediction. We don't really know how confident our model is in those predictions. It's just kind of giving us a number and we're taking it at face value. So it would be convenient if we could use a flexible method like gradient boosted regression trees, but also had some more information about, well, how confident are we in this runner's time? We can get a prediction that maybe some runner runs 170 minutes, but is it within 165 and 180? Or is it maybe within like 100 and 200? What's the range that we're looking at? And so these challenges are what BART can answer. So what is BART? It's short for Bayesian Additive Regression trees, and it's a flexible non-parametric model. And the whole idea is we're just trying to estimate some unknown function f. F is this function that we believe is the response of y, and we're going to try to see what that looks like. Now we're going to make some assumptions. We're going to make an assumption that the error is normally distributed, which most statistical models have this baked in. That's actually not a particularly strong assumption compared to all the other tools that we use. The difference between BART and something like gradient boosted regression trees is to handle the regularization, which basically just means the shrinkage to prevent us from overfitting. Instead of using cross-validation, we're going to use Bayesian priors. And in the function right here, these G terms, that's reflecting the regularization properties of the prior. So each regression tree gives a prediction. They're called terminal nodes or leafs in kind of the regression tree literature. So for each tree, we have a series of predictions M. Now we can follow an individual down the tree, and it's going to give us their prediction. It's the same thing we saw earlier when I talked about making those cuts. We just see, well, if we just have one cut, what side of the cut are you on? And then depending on what side you're on, your prediction is just the mean of that group. And that's what we mean by these T and M terms. So for each tree, we're going to follow it down the sequences of cuts, and then just see which group you're part of, and that's going to be your prediction. Now, just like gradient boosted machines, we're going to add all these terms up. So we're going to have a bunch of small trees that make teeny tiny predictions, and at the end of our process, we're just going to sum it all up, and that's our prediction for an individual. Now, instead of using an explicit learning rate, this G term, which is really a combination of a few things, is going to prevent our predictions from getting too exciting, getting carried away. So how does this actually work? Well, the priors are really doing a lot of the work in BART. Now we have a system in which trees are actually going to be proposed and they're going to be accepted or rejected. This is different than what GBM is doing. In GBM, it's just fitting trees. Now, what does it mean to propose or accept a tree? It seems kind of nuts. So the idea is, well, we start with something like the mean, and we could imagine fitting a tree that is better than the mean. And so we're going to use a kind of predetermined subset of rules, and the algorithm's going to randomly pick one and say, you know, what if we added a split here? And it's going to say, well, how would this split do compared to what we had before? And with some probability, that's either going to be accepted or rejected. And it's going to be done so in such a way that we're gradually going to favor trees that improve the fit. And this is how we kind of trade out traditional hyperparameters for things like for tree depth and learning rate for Bayesian priors. Now, let's think a little bit more about the beliefs we might have for regression trees. For those of you who are kind of from a traditional, have heard about traditional Bayesian statistics, this seems kind of nuts. People are used to picking priors and like a regression coefficient. Like you have some idea about a reasonable range for a coefficient to be, and so you put some probability distribution on that coefficient, and it's going to calibrate and kind of restrict how carried away your regression can get. So how does this work with regression trees? Well, we actually have some pretty concrete beliefs about how regression trees should be behaving. Now, we actually know that we should be pretty skeptical about predictions that are really far away from the general mean. Like we said, if we didn't have any other information, the best we could do is the average. So we should be pretty wary of things that are really, really extreme. That could be a sign that we're starting to overfit. We also know that trees should be pretty small. This is the whole mechanism of how gradient boosted machines works. By keeping each tree small, we're preventing overfitting. So we already have a belief that they're supposed to be relatively constrained. This is not shocking at all. And we also think that our model should outperform linear regression. We're not making any traditional parametric assumptions in the shape of f. F could be whatever shape it wants to be. It could be a step function, it could be a curve, and we're thinking that we can model that and that we can represent that function pretty well, certainly better than a straight line can. And so these are the ideas that we just need to break into priors. Now, how does this actually work? Well, the critiques and one of the challenges of Bayesian statistics is how do we pick the priors? Sometimes in some journal articles, for example, referees may be wary of, well, did you get the result because you just picked a prior, and maybe the prior is playing an outside influence over a result, and what would have happened without the priors? And there's this idea that our priors are kind of representing our subjective beliefs. Now, all of those things certainly can happen, but there's other ways to think about setting priors. And if the priors have such a big role in the process here, how are we choosing them in a principled way? So it turns out, with what we're doing with BART, the priors are actually calibrated from the data, largely, which is really helpful for us. It means you guys can use BART without a strong knowledge of setting Bayesian priors. And one of the convenient features of this algorithm is the default priors are going to work remarkably well. So much so, we're using BART with the default is going to perform as well, or if not better, than existing machine learning methods when they've been tuned thoroughly. So we can kind of use it off the box and get really, or out of the box, I should say, and get really, really strong performance. And that's a big advantage because we can maybe get a good estimate right away of how good our model would be doing without spending hours or weeks that we'd be doing a massive grid search. We don't have to worry about setting up a Bayesian optimization way to hypertune things. We can just perform pretty well right out of the gate. Now, this is all for continuous outcomes. You can use BART to make predictions about binary outcomes. Things get a little bit trickier there, where you'll have to do some more work, maybe cross-validating a specific prior, which we'll talk about in a little bit. But for continuous variables, the calibration is going to give you a really good answer right away. Fortunately for us, what we're going to be talking about later on too in the implementation, even for binary cases, there's some tricks that are already built into the package that's going to help you get a good answer without having to know a whole lot about probability distributions or about setting Bayesian priors in general. So this algorithm is a little bit less intimidating than, say, using a Bayesian regression, where you explicitly need to use distributions and have a lot of knowledge about how to specify thoughts that you have and beliefs into the actual estimation process. Whereas here, we're just using the data we already have to kind of enforce our beliefs that we already know about regression trees. And these beliefs are going to be the same in essentially every problem we have in the socio-medical sciences. We know that really, really deep trees are going to overfit. It's just a process of how the trees work. So there's 3 priors. The first, and arguably the one that's doing the most work for us, is the prior on mu. Sometimes this is called the prior on the means. Now, when we actually fit these things under the hood, at the beginning of the process, it's going to rescale your data. So it's going to take your outcome and say, okay, we're going to apply a transformation and kind of make it so everything's between negative 0.5 and 0.5, and we're going to set the mean to 0. And this is going to be really convenient. It's going to help us kind of calibrate our priors without the user having to put in a lot of work. And we also know that for each kind of terminal node, which is just a fancy way of saying for each of our predictions, we want mean to be distributed, or the mean to be distributed normally at 0 with a standard deviation of sigma squared, or with variance sigma squared, I should say. And so for each individual, well, it's just a sum across all these little terminal nodes. And so we can apply some knowledge about this to shrink in extreme cases. The idea is to set this mu prior so that 95% of our values fall within maybe negative 0.5 and 0.5. We know that things shouldn't be too extreme. We don't want things getting too far away from the mean. And so if we use this kind of knowledge that we have, it's going to give us, it's going to make this probabilistic statement true. And so the default value in here is a k value of 2. This prior is called k, this kind of prior on the means. Now, like I said, it's going to work really, really, really well out of the box. And if you're doing binary predictions, the package you're going to use has a lot of tools built in, so it's also going to work really, really well out of the box. Still could be a good idea to maybe do some cross-validation, but you're going to be starting from a strong position. And like I said, the idea here is we're really going to keep our nodes from getting too extreme. Each of these groups, it's going to be kind of reined in. So if it starts to give predictions way beyond this 0.5, it's a sign that the regression trees are getting a little bit too sensitive, and it's going to squeeze things back in. Again, the big takeaway from this slide, you don't need to understand all of the math or all of the kind of baked in probability assumptions. It's just we want things to be generally closer to the mean, and extreme things are going to get squeezed back in. We can also set a prior on tree depth. So we can use a distribution, and it's going to kind of determine how likely we are to propose different trees. So as I said, we're going to be kind of proposing trees, and they're going to be accepted or rejected. Well, what's the depth of these trees going to be? We can kind of rein that in. And as I said, we want to keep our trees relatively small. Remember, the higher the depth, it means the more cuts we're making. Depth is another way of saying just make additional cuts. So we can say, well, we know we should probably have at least like 1 cut or 2 cuts. So maybe we want a high concentration around 2. And this number, so I should also say BART was initially invented by Chipman, George, and McCulloch. They were 3 statisticians that developed the actual algorithm. And they explored a lot of these different combinations and set on this number, and it worked really well for them in practice. And so the idea is, well, we're saying it's really likely to have depths of around 2 or 3, and less likely to get into 4 or 5, and also less likely to be 1. We're going to need some depth, but once we get beyond this kind of 3 point, it can get carried away pretty quickly. Now, the important thing to know, though, is if it turns out that for whatever problem we're modeling, maybe we need deeper trees. If the data demands it, the trees will get deep enough. So in the initial paper about BART, they explore a bunch of these trees, and they actually recorded a depth of 17 on one of them. So it can get pulled deeper and deeper and deeper if proposals that add depth continue to be accepted. So the prior isn't a hard cutoff. It'll allow us to still move flexibly. It's just going to need to see a strong signal before it gets too excited. So the prior on means is about pulling predictions inward. The prior on trees is about keeping our trees nice and shallow. Again, all this stuff's encoded in the default. I'm just more putting it here to give some context on how we're going to be making these good predictions, and the mechanisms that are in place that's maybe making it less necessary to cross-validate these parameters. Like I said, sometimes cross-validating that mean parameter k can be helpful. Generally, in practice, I've had a lot of work with this algorithm. Usually, I have not looked at ever cross-validating the priors on the trees. And our last prior is going to be this prior on sigma. And we had that last kind of belief that we really think we should be doing better than a linear regression. And so at the beginning of our process, we're just going to fit an OLS, ordinary least squared regression, and we're going to see how well we're going to do. Now, it's going to give us a conservative benchmark of saying, well, like even if it really was like we're only doing as good as regression, how good is that going to be? And we think that we should have about a 90% probability that our sigma is going to be smaller than from OLS. And so we can encode that into the prior, and it's going to help us kind of determine this last little piece of the puzzle. Again, this is one where the default I would feel very confident using. Most of the tuning that happens in these models is all on that mean. So the whole process, kind of like in gradient boosted trees, we're going to start with the mean. And we're going to propose a variety of trees. Maybe it's we're going to grow a new tree, or we're going to prune a tree, or we're going to flip a tree. We're going to add a split. We're going to change these trees around. And there is a pre-specified number of trees we're going to go. Usually it's about 75, and that's kind of hard-coded in. You can add more trees if you'd like. Usually the range is somewhere between maybe 75 and up to 200. But generally in my work I use around 75. And these trees are going to be accepted or they're going to be rejected. So we'll propose a new split, and there's some probabilistic method in the algorithm that's going to determine if that split is accepted or not. And we're going to be favoring acceptances of trees that improve our fit. And we're going to do this again and again and again and again. We're actually going to do this thousands of times. And we're going to throw out a bunch of the times from the beginning. It's called the burn-in phase. And because at first, our proposals are probably not going to be great. There's some randomness here, and we kind of need the algorithm to warm up for a little bit. So after a sufficient warm-up period, we have a whole bunch of runs through this algorithm. Like I said, there's about 75 trees. So we have 75 trees, and it's going to fit. It's going to propose more trees, and it's going to keep making proposals, and it's going to propose and propose and propose. And these are called iterations. And so after thousands of iterations, we believe that we have a pretty good estimate of F. Now, one fact about BART that's a little bit different than GBM. In GBM, the ordering of the trees is really important because each tree is essentially predicting on leftover from the last tree. So in BART, all the trees are actually exchangeable. You can move around the order and get the same result. And that's because we've ran it so many times through these iterations, and each proposed tree is kind of conditional on all the other trees that came before it. So because we've already conditioned on all of the prior trees, we can move around the ordering of the trees, and it's not going to change our predictions from this sum. Now this was a very, very long warm-up to get to, well, how did we actually do? So with a BART model, our in-sample RMSE is going to be around 11.2. which is pretty good. We've seen some other in-sample predictions that have been lower, but when we look at how they perform on out-of-sample data, it gets much worse. I think regression trees, you can get them to really overfit. And so they can fit really, really good. In fact, they can fit perfectly if you continue to make more and more and more in cuts. And the problem is what happens when you see out-of-sample data. Now here, our jump when we go from our training set to our testing set is the smallest we've seen so far. And to date, this is the best prediction we have. So our RMSE here is about 12.2. And so we're making better predictions than GVM, better predictions than all of the things before us. Now, the classic issue with using these simulated examples, and I simulated this data myself as well, did you just make up some data that kind of fit your use case? And so there's been some work on comparing BART to other existing algorithms. Oh, and actually, we're going to get to that work in a second. I also made a little bit of a generalization. So when I showed this, we have this nice little prediction line. BART's actually making distributional predictions. So we're making a prediction, a probability distribution for each point. So we can draw the line that is the average, or we can also think about, well, what is the distribution of our predictions for each given point? And this is going to be really, really convenient because sometimes we don't just care about the point prediction. We want to know how confident our model is in that prediction. Your opinions about a model may be different if you say, well, we're predicting, say, a time of 150. Now, is that prediction between maybe 145 and 155, or is it between 100 and 300? Those things should mean very, very different things to when you're working as an applied modeler. We prefer models that are probably a little bit more confident in their predictions. Now, there's other ways you could get these types of results using traditional machine learning methods. You could use various resampling techniques like the bootstrap or the inferential jackknife. All those things can get at similar issues, but the problem is that's going to be incredibly computationally demanding. BART just spits this out as a process of estimation. So we have this built into how the algorithm is actually making predictions. And we can use this not just for predictions, but it's also going to be really convenient if we want to use machine learning models for inference problems. Now, as I saw, and this picture got cut off a little bit, it's possible that maybe I overfit BART to the ones who developed BART. They tested out the algorithm over 42 data sets and 800 trained test splits. And they looked at BART without cross-validation at all and with some cross-validation to things like that prior on the means. And so what we see, and they compared it to other top performing algorithms at the time. Boosting is just a term for gradient boosted machines. They use neural networks, random forests, and I believe one other algorithm that got cut off. I think it is support vector machines also. But so what we see is when you use BART out of the box, BART default, it's performing as well, if not just a little bit better than the existing models. And when we cross-validate BART, that prediction gets even better. So across a wide variety of data sets, we're seeing really, really good performance, even without spending a lot of time cross-validating. And I should say all the competitor models were fully cross-validated. So we're kind of giving them the most favorable treatment and just pulling BART straight out of the box. Now, all of this seems a little bit abstract. How do we actually use the thing? So I'm going to be talking about what a lot of my work is about, which is using the dbarts family of packages to actually address applied problems. Now, what are these problems? Sometimes we're interested in prediction problems, sometimes we're interested in inference problems. And the dbarts family of packages, it's really 3 packages, and the dbarts package is kind of at the heart of it, is going to help answer each of these challenges. Now, there's definitely other approaches. In no way do I want to say that BART is the only solution, but it is a tool that you can use in your toolbox and one that has a lot of advantages, in my opinion. And I also want to give credit to my colleague Vince Dory. Vince Dory was the developer of the dbarts package. A lot of my work is on applying the dbarts package and its kind of other its family of packages to work in causal inference. So a lot of my work is seeing how these things perform in the causal inference space. But this was developed by Vince Dory, and a lot of his work has been cited. So how do we actually fit one of these models? Now, the inspiration for this talk is I've given talks about BART in the past, and it's this kind of high-level version where I'm just talking about, oh, here's how the algorithm works, here's how it performs pretty well, but how do you actually use the thing? And it turns out, I had a lot of conversations with people after some of these talks, how to actually use the thing can be a little bit confusing. There's documentation out there, but it can be very, very dense, it can be hard to read, and there's a lot of things that may not make sense if you're not steeped deep in the space. Like, first of all, the first step is downloading the package. So you can download the dbarts package from CRAN, or you can install it from GitHub directly for the most recent development version. So if you want to fit a BART model, here's confusing point number 1. There is a function called BART, and there is a function called BART2. You want to use BART2. BART is the initial kind of implementation that has a lot of the defaults used by Chipman, George, and McCulloch. BART2 is this kind of expanded version that has some more in-depth defaults worked into it. So for example, if you fit BART2 with a continuous outcome, its default prior on the means is going to be set to 2. And that's that value that we know is working pretty well out of the box. Means we expect 95% of our cases to be within 1 standard deviation of the mean. Within 2 standard deviations of the mean. Within 2 standard deviations of the mean. Now, as I referenced earlier, binary predictions get a little bit harder. Now, BART2 has a very, very sophisticated kind of guess at what k should be. Binary outcomes, you want to tune k a little bit. Now, BART2, when you have a binary outcome, it's going to know it's a binary outcome. It checks if it's binary or not, and it's going to use this kind of built-in hyperprior. It's not a set value of k, it's going to estimate a good value of k. And so it's going to change k for you for binary variables, so you can still use it out of the box. If you're really trying to get maximal performance, I would cross-validate k, but out of the box, it's still going to perform pretty well for binary or continuous variables. But the original BART without the 2, it's not going to do that trick for binary outcomes. So that's one reason why you might favor using BART2. And we're just going to model it like a linear regression. The syntax is essentially the same. We can pass it a data frame. In this case, runners 1 has been the data we've been working with up to this point, where we just have our prior race variable and our variable for whether or not runners are wearing the hypershoe. And we can get predictions for outcome marathon running times. Now, sometimes we'd like to make predictions for future data. So there is an argument, keep trees. Its default is false. If you want to make predictions to data that you do not have yet, you're going to want to flip that to true. There is a predict method. You can use the predict function and pass it new data, but only if keep trees is set to true. Now, some might ask, well, why would you make the default false? So when you save all of the trees, it takes much more memory, and it takes much more space. Now, if you already have a data set that you want to, like say a test data set available, and you're just trying to see how it would perform out of sample, there are ways to do that without using keep trees. But if you want to use this stuff to make predictions on data you don't have yet, and you're training a model that you would like to maybe deploy for other things, you're going to want to set keep trees to true. One of the problems of scaling this stuff is, like I said, it is very memory intensive, and that is why the default for this is going to be false. So if we want to get predictions from our training set, if keep trees is set to true, we can just use this predict function. And actually, this is going to be the test set here. I said training, but we want to do test. You can use this for training or test sets. Now, there's an argument for type. So we're going to pass it our model, in this case fit1. We're going to pass it if we want to make new predictions. It's going to be new data, and we're just going to pass it our new data set. If we leave that blank, it's just going to give us our training set predictions. Now we have a choice to make for the type of predictions we want. Now in Bayesian statistics, we get predictions from what's called the posterior predictive distribution, or we get the expected value. My advice would be for just general predictions, particularly if you have not seen, if you're trying to use this to make predictions for data that you haven't seen yet, you want to use the posterior predictive distribution. What that's doing is just adding in more uncertainty. And it's the fact that we might, there's more uncertainty about predicting things we haven't seen yet. And it's going to account for that, and it's going to make our predictions less confident. Now, if we look at what our predictions are, if we did this in a linear regression or a gradient boosted machine, we just have a vector of predictions. So that's not what we have here. We're actually going to get a matrix. Now, what's going on? So we have 800 runners in this data set, and we have an 800 by 2000 matrix. What's the 2000? So remember how I talked about how we're going to iterate again and again and again, and we're going to fit 75 trees, and then we're going to fit 75 more trees, and we're going to keep fitting trees. We're going to do that about 2,000 times. Now this has already removed that kind of warm-up step. In fact, we've done it more than 2,000 times, but it has already removed that in default because we don't want to use those. We know that it's not ready to be used yet. So these are all of the different iterations we have, and we're going to use, this is the information we're using to make those kind of prediction bands. In this case, we have 2,000 rows and 800 columns, and our columns are going to be our individuals, and our rows are going to be our iterations. So each row of our matrix here is a different prediction from a different iteration, whereas each column is a different individual in our data set. And we can use this to do a variety of things. So let's say if we just wanted the point prediction, if we just wanted our best prediction for each person, well, we could just take the means over the columns. Remember, we have 800 columns, those are individuals. If we average over, we now have a prediction for each individual. Now we just have a vector of 800 after we average over the columns. And so if we wanted the prediction for runner 10, we can just look at our point prediction. We can look at the 10th individual in this vector and see that our prediction is about 292 minutes. And so these are the tools you can use to extract an individual's prediction when you just want the best prediction. You're less interested in, say, what's the range of these predictions? What range could these predictions take on? We could also, as I said, it's a distribution. I think when we look at the line bands, it can be a little bit misleading of the actual probability mass. And so we can look at the range of predictions for runner 10. And as we see, the mean is right in the center of this prediction. It is our best prediction. It's the best prediction we can do. But there's a whole range. It could be as low as 240 or as high as 340. And the nice thing about doing this in a Bayesian framework is we can interpret this how our common sense would dictate. We can say that there is a probability of a certain amount that our prediction is going to be in this range. We're avoiding some of the more, we're not really thinking about null hypotheses, we're making direct probabilistic statements. Now we can easily use just built-in R functions like quantile to look at the range, say a 95% credible interval. We can easily calculate a 95% credible interval, again for runner 10, and we can say, well, we're 95% confident. I mean this in, we're 95% confident that our prediction for this runner is between 267 and 317. So I talked about tuning the means. Even though we're going to get pretty good performance for these continuous predictions right out of the box, what if we actually want to tweak this k value? So there is a built-in function into the dbarts package called xbart. And xbart is what we're going to use to tune some parameters. We can just give it a grid of parameters for what we want to tune, and it's going to do the cross-validation for us. It's going to do, I think the default, it's a little bit dependent on how big your data is. And with 800, it did 21-fold cross-validation. And so we can set up a grid for k. To save time, I kind of dialed it back. I started with 1 to 5, and I changed it to 4 to 5 because I already know what the best answer is. In practice, I would start at 1 and maybe go up to 5. Maybe, as I said, the default's going to be 2. But in this data set, our best value of k is actually going to be 4.9. K can be kind of high sometimes. Like I said, it depends on your data. The difference between our kind of off-the-shelf version of this version isn't too big, but it's a little bit better. And so we can run this xbart. It's going to spit out a matrix. We can just average over all of it and see what our minimum k value is, or see which k value gives the lowest RMSE in this case. It's going to default for continuous variables to give you, we're trying to get the lowest RMSE for a continuous predictor. And so we see that maybe our k is not what we want to do. How do we refit BART2 with a different k value? So fortunately for us, this is pretty straightforward. We can just pass it. There's an argument for k. It's going to default to 2 for continuous variables. But if we wanted to change k, we can just specify a different number. And we can use the built-in xbart function to let us know, well, what would a better number be? You may also notice that I have this verbose flag to false. That's just for the sake of these slides. It's going to spit out a bunch of information. It's going to tell you what all the priors are. It's going to give a count of how many iterations you're at. It's going to give kind of a countdown of how much longer is left in the modeling process. So for the sake of these slides, I've set it to false, but you don't have to think too much about what that parameter is doing. It's more of just a stylistic thing. Again, I'm keeping keep tree set to true because I'm going to be making some predictions out of sample. And so now, if we look at how we performed, strangely enough, our test set actually got better. We could look at a, again, the label, you can see the label's a little bit off, but we're still now even making even better predictions. This is the lowest we've seen up until this point. Predictions around 11. And we're seeing that estimating that percent of the time to cross-validate the k is really improving our predictions here. And so that's just the basics of kind of getting going with using the dbarts package for your own models. But sometimes we want to do different types of models that are maybe a little bit more sophisticated. Some of you may have heard of partial pooling. Now, say that we have a factor variable like country. These are runners who are running a marathon. We may track what countries they're coming from. In big races like the Boston Marathon, we have people from all over the world coming to run these things. And so we can extend the existing BART framework to accommodate for things like partial pooling. So say we have this variable country. Now it's possible that in our training data, we may only have people from a limited number of countries. And we may want to make predictions in the future, and people may come from countries we haven't seen before. And so in a traditional framework, we'd be kind of stuck. Like if we just modeled this as a fixed factor and then say, next year we see somebody from country code 64, your model's not going to know what to do. And now partial pooling, instead of treating each of these things as fixed, it's going to look at it as kind of a population. We're going to say, well, there's some distribution of countries. We're going to model the variance instead of the means. Now, so if you wanted to just add a term and use this in what's called the full pooling approach, this is kind of the traditional, if we just put it as a predictor, we just add it to our, just like a regression. We're just going to add a term for country and fit everything else as we had before. Now, if we want to do something a little bit more sophisticated, we're going to bring in some heavier machinery, the stand for BART package. The stand for BART package is built on top of dbarts. It's using dbarts to model the means non-linearly using BART, and it's using stand to actually parametrically model this random effects term. And so what I mean by partial pooling is, say we want to fit a random effect, but want to have a non-linear mean. We can do that with the stand for BART package. And it uses just traditional LME4 style syntax. And so we can just put the terms that we want BART to model in this kind of BART section of our call. We have a stand for BART function. We specify our outcome. We're going to say what we want to model non-linearly it means. And then we can pick, using this kind of traditional one bar random effects LMR syntax, we can say that we want to fit random intercepts for country. And this is going to give us a partial pooling approach. And so what does partial pooling actually mean? This, for those of you who aren't familiar, well, it's going to improve our predictions. It got cut off, but the non-partial pooling on the left is giving us an RMSE of around 12.7, and with our partial pooling, we're down to 12.4. I should say this is slightly different data. I've edited the example a little bit. That's why predictions are a little bit higher. This is a little bit harder to model. So why would we want to use this thing? Well, we can account for unseen future groups, and we can make predictions for some hypothetical unseen country that we don't have. We could account for non-IID data. We're making this kind of independence assumption. What if we have inherently dependent data, like students nested within schools and nested within classrooms? We can account for that nesting. It's going to further regularize our predictions, which can improve our predictions, and it can be more efficient. Now, all of this is making some independence assumption about the relationship between the random effect and the fixed effect. Beyond the scope of this talk, but there's a really good summary of it in Gelman and Hill, 2007. And the types of situations in which this partial pooling is really, really effective is when we have a big discrepancy in the size of our groups. So we have a ton of people from country code 40 and one or two individuals from, say, country 11. And so we have these big discrepancies in the representation across countries. Fixed effects may overfit a little bit. And so I'm simulated some data to give an illustration of what partial pooling is actually doing. So again, this black line is just, if we just made a prediction from the mean, that would be our prediction. And these blue points are if we made the traditional kind of fixed effects approach. We're just putting our country term in as a predictor. And some of these terms are pretty extreme. And the size of each of these points is kind of proportional to the representation. And so we see that some of the most extreme points are actually these relatively underrepresented cases. And it could be that because there's so few people in there, we're kind of overfitting them with the fixed effect. And so what a partial pooling solution is doing is it's pulling in all of the predictions to the general grand mean, and the amount of pull is proportional to the size of the group. So we see individuals like this who are really extreme and really small get regularized a lot. Whereas even some moderately extreme cases down here that are big are getting regularized a little bit less. So our model is a little bit more hesitant of underrepresented groups, particularly when they have really extreme predictions. And again, this fits the theme of this belief we have that things should be pretty close to the mean unless we have a lot of reason to believe that they aren't. Now, how do we actually work with these predictions? Again, with stand for BART, we can just run some simple line of R code to extract the predictions. I am wrapping up. I know we're getting a little bit over time. And so we can just extract our predictions. Again, we have this 800 by 4,000. There's a few more iterations built into the default of stand for BART. Generally a good thing. There's kind of more going on. We want a few more iterations to get the algorithm going. You might notice this T here. Because we like to keep things complicated, it's actually reversed for stand for BART, the rows and the columns. So I like to use this T just so everything's all on the same page. So we have individuals in our columns and iterations in our rows. Now I'm going to jump over this. This is just some R code. I'll post these slides so people can see how to extract these things. We can write a whole bunch of R code to extract, say, predictions for each country. And then we can plot it. So we can make plots of each country's average running time. So we can average over countries and then make statements about, well, which country do we think is faster than the other? And then we can actually just calculate the probability. So looking in at, say, country 12 and country 31, we see they tend to be probably the slowest countries here. Which one is slower? And so we actually know that country 12, there's about an 83% probability that it is slower than country 31. And we're just dividing by the number of iterations. And so we can make some statements. This is getting into the inference space now, where we can actually make comparisons about groups and put a probability on it, instead of just a point prediction for each one. And we're using the wealth of information we know about the uncertainty of our predictions. And we can do the same thing with individuals. Again, just with a few lines of R code, we can calculate 95% credible intervals and point estimates for all the individuals in our data. Before we were looking at countries, now we're just looking at individuals. Now, how is this stuff used most in my work and in the world at large? BART has remarkable uses for causal inference. It's a its most popular application is in the causal inference space. And what is it? Well, when we think about a cause, we really are thinking about two potential outcomes. In the case of the hypershoe, now some of you may be wondering, can we actually say, does the hypershoes cause people to run faster? If we've been kind of looking at these images, maybe it's hard to say. Now, we could think of what would have happened to a runner, what would a runner's time been, had they not worn hypershoes? And we're going to call this Y0. And we could also ask, well, what would their time would have been if they did wear hypershoes? And we're going to call that Y1. And the problem is we only ever see one of those two things. But what we can do is we can turn this into a prediction problem. And we can say, well, if we're missing a potential outcome for each person, what if we just make a model and fill it in? And that's the idea with BART for causal inference, is we're trying to impute those missing counterfactuals. And if we have a flexible enough model, and if a few structural things are true, we can do it. Now, BART is not magic, and I don't want to oversell it. There's a lot of work going on to continue to try to improve it, particularly and explore what it's good at and what it's not good at. But it is not going to work for causal inference if we have confounders that we haven't measured. We're making a really strong ignorability assumption that, well, if we've collected all the confounders, and if we know what all those confounders are, we can model any nonlinearities that exist. We can pick up any interactions in the data. But we can't fix what we don't have. We can't magically identify confounders that we haven't measured. We're also making a Sutva assumption and an overlap assumption. Again, a little bit beyond the scope of this talk, but the short is we're making some spillover thing. We're kind of saying that each treatment is kind of affecting an individual specifically, and that, say, people who are in the control aren't being affected by people near them who were in the treatment. And there's overlap assumption, just saying we have individuals that we can use to model. We need some people in the treatment group and in the control group in the same part of the covariate space. Now, they don't have to be weighted the same. They can be, we can have a ton of people in the treatment and very few people in the control, say at the lower end of our predictor, but we need somebody there. And so if we go back to the very beginning and we just fit a linear regression, what would our causal effect estimate be from a linear regression? And you can look at the coefficient, and it's actually saying that hypershoes make you slower. Now, do we believe this or not? I don't know. I mean, maybe we could buy it. Like, if we fit a BART model And there's a specific package, BART cause, that's going to handle the causal inferences pieces for you. It's going to do all the extraction. We see that hypershoes in this case actually do cause you to run faster. But we would not have picked up that effect if we relied on traditional linear models to estimate them. Now, this is just the tip of the iceberg. In the space of causal inference, BART has applications in saying, well, is the treatment effect different across levels of X? In this case, looking at our graph, we certainly can see that it is. Traditional models would have a harder time estimating that. But because we have all the added flexibility of BART and the inferential properties, we can pick up nonlinear treatment effects. But we can even still estimate our average treatment effect, even when the data is highly nonlinear. And so that's the talk for today. Like I said, just the tip of the iceberg to all the things that are possible with this algorithm, and looking forward to future conversations around how you can use it in your own work.
All right, I will kick this off with a virtual question. Then I'll see if we have questions in the room, and we can go back and forth a little bit depending what it is. If there's a question in the room, please repeat the question because they are not mic'd up.
All right.
All right. So, in terms of Stanford, BART, and dBART, what benchmarks exist in case of large data? I'm going to stand
So Stanford BART is really slow. It's really slow. It's a big problem with it. Define what you mean by large data is kind of the question, like how big is large? It's very new. The first paper on it was actually just published last year in Entropy. And it was specifically looking at the causal inference space. So it's very, very fresh out of the box. So I don't think a lot of benchmarks exist at this time.
How about dBART itself then?
dBarts?
Yeah.
Yes, so dBarts, again, most of the dBarts performances have been really looked at in the causal inference world. So at the American Causal Inference Conference, there's a data competition, and BART-based models are annually the top or one of the top performers. And so what they do is they have many, many, many thousands of DGPs. I think in 2016, where there's a paper by Vince Dorey, Jennifer Hill, Mark Scott, and others, where they basically look at, well, in this competition, we've got 7,700 kind of different data sets. People submitted different solutions, which ones did the best. That year, BART was the top performer, and it's essentially what the same kind of under the hood things that became dBarts. And there are some other algorithms that again, like state-of-the-art stuff that perform very, very well too. But every year at ACIC, it's one of the top, if not the top.
When you say one of the, I just follow up for the person. And when you say one of the top, do you mean in terms of predictive power or in terms of speed?
Oh, predictive power. It's relatively slow.
So dBART, so like let's say dBARTs compared to XGBoost. Which one would do better predictive? Which one would do better speed?
So I mean, I feel I don't want to off the box say, well, this one's going to be better, this one's going to be other. BART's probably going to be slower. dBarts is remarkably fast compared to the older implementations. Another reason to use it. One of the reasons it was created was to make it aggressively parallelized. So the initial implementation is much, much slower. This one's taking advantage of all the cores on your computer and is doing it as efficiently as it can, but it's going to be slower than something like a gradient boosted machines because there's just more things being modeled. And we have this whole Markov chain Monte Carlo happening under the hood, computationally very intensive. So I feel confident saying that dBarts is definitely going to be slower than like a gradient boosted tree, but dBarts is definitely faster than the older implementations of BART.
Then I'm going to do one more follow-up for this person then, because I guess I'm following up, not them. Actually, they are asking, aggressively paralyzes music to their ears. It's so aggressively parallelizable, can you do it on a GPU, so like XGBoost goes on a GPU?
To my knowledge, no.
All right, cool. All right, I will turn this over to a question in the room. We'll do a few room questions. We'll go back to virtual, go back and forth. Anyone have a question in the room?
I have a question. So you went over the partial pooling and used country as an example. How does the model take into account the population of each country in
Yeah, like
repeat the question. Repeat it.
Oh yeah. So I talked about partial pooling with countries. How does the model take into account the population of each country when fitting the model? So review of multi-level models. Again, it's like do you mean taking into account in terms of like how does it actually do the partial pooling?
No, like does it take into account like if let's say one country only has one?
Yes, that's exactly what it's doing. Yeah. So it's basically saying, well, there may only be one person in this country, and so instead of just like what a fixed effect model is doing is it's going to say, well, like the mean for this group is this person's thing. And that's our effect. So what partial pooling is doing is at a high level. Now the specifics of this I'm not going to be able to answer in the Q&A, but at a high level it's saying, well, if you are one of these underrepresented countries, where say there's only one, you're the only person from your country 10 in the marathon, it's going to poll your score closer to the mean of everyone. And you're going to get polled more than people that are from really represented countries. So if you're from a country that's really well represented, like say Kenya, for example, this is an actual example, where there's a fair amount of Kenyans running the marathons, and they all do remarkably well. Like I think last week actually, the world record was set by a Kenyan runner. I think they ran 2 hours and like 30 seconds, which is remarkably fast, like faster than I could run a mile for 26.2. I think it's like 4:16 split, like crazy speed. But so if you have a lot of people from a country that are really extreme, it's not going to pull you that much because it's like, well, we have a lot of cases. Like it's something going on here. Whereas if you're just one person, could be a lot of things going on, so you're going to get regularized more. Mm-hmm. Yeah.
Do you have another in-room one? We do another one in the room before I go back to virtual?
Yeah, so one thing you said a little bit earlier was when you were comparing dbarts to sort of like cross-validated grid searches.
Yeah.
You did sort of say that, you sort of implied that dbarts would be faster than doing those sort of cross-validated grid searches. My question really sort of follows from that. It's like, how sensitive is burn-in time and model flexibility to the specification of the priors?
Yeah.
Repeat the question.
That is a good question. So
We're so good to repeat it.
Oh yes. So the question is, how does burn-in time factor into the specification of the model? So in the case of, and to get a little bit into the weeds, if you look into things like convergence, BART models actually don't have great convergence in terms of things like the marks set up by the Stan development team. They have known mixing issues. In the case of just normal dbarts, it seems to converge pretty quickly, but the normal dbarts is still fitting relatively quick. It's one of those things, it's slow if you're doing a simulation study and you're doing thousands of these things. It's certainly slower than regression, but a single model will take a second or two. So it's not, and it'll scale some with the size of data you're using. The Stanford BART is much slower because there's just more going on. There's an HMC step and a non-HMC step, and so it's the Stan part makes it really slow. And I think Stanford BART is a little, and there's some exploratory stuff that I'm doing related to this right now. The Stanford BART is a little bit more sensitive to iterations and burn-in and things like that. But the dbarts one is pretty quick off the shelf.
Do I get a follow-up?
Sure.
Do you run multiple chains and then check for convergence?
Yes.
Okay.
Yeah. And for people who know more about these things, you the default is 4 chains for dbarts. For Stanford BART, I usually run 10 chains. If you're doing Stanford BART, you want to do more. BART Cause actually does 10 chains too. The default for just dbarts prediction is 4 though. So it's kind of automatically doing multiple chains. There's a built-in plotting function if you want to plot chain convergence.
Awesome. Thanks so much.
Yeah, but you can see that if you check the convergence, it settles down pretty quickly. Mm-hmm.
To follow up on you, is dbarts itself using Stan also?
No.
So what's doing the Gibbs sampling in the HMC?
It's a sampler. There's no HMC in dbarts.
Okay.
dbarts is it's a Metropolis Hastings and within a Gibbs sampler. Mm-hmm. So it's a Metropolis Hastings for proposing new trees, and the whole thing's wrapped in a Gibbs sampler.
Is that in C++ or is that in
Yeah,
R?
it's written in C++.
Okay,
yeah.
so
it's all in C++. dbarts is mainly written in C++, and it's the R interface to the C++. BART Cause is fully written in R, and it's the wrapper for dbarts for doing the causal inference stuff, because there's a lot going on for the causal inference about like what gets modeled which way. Like for the things we see, we use the things we see. For the things we can't see, we need to make predictions. It's default doing kind of what you would want it to do in terms of like when should you use the posterior predictive distribution, when shouldn't you do that. Also plug, there's a point and click interface for BART cause called thinkCausal. Whole different thing, but if you don't want to use R at all, you can use point and click and thinkCausal.
Cool. And what's that written in?
What?
What's that written in? thinkCausal.
R and tiny.
Nice.
Yeah, so it's the low-level C++. Stan for BART is using Stan and using dbarts, and they're kind of it's Stan for BART. Yeah.
Then we got a virtual question. I thought original BART paper, the original BART paper, terminal nodes are deterministic average of observations in that portion of the tree. I think you mentioned terminal nodes are normally distributed. Can you clarify?
Yeah, can you repeat that? Sorry, I didn't catch it.
Do you want me to? I'm on the mic.
Oh.
So to repeat it for you or for the audience?
Yeah, for me, I didn't hear the question.
It might be easier if you read it.
Yeah.
That's a really involved question.
Okay, let's see. Whoopsie.
You want me to go back to it?
I hit the wrong thing. Let's see. I thought the original BART terminal nodes are deterministic average of the observations in that partition of the tree. I think you mentioned terminal nodes are normally distributed. Can you clarify? So yes, the terminal nodes are deterministic, but in like when they're being sampled, like the likelihood has a Gaussian.
Okay.
And the error is definitely the Gaussian part. So when you add in the error, you're getting, like if you're using the posterior predictive distribution and bring in the error, that has.
So like a linear regression is a deterministic mean, but it is still normally distributed.
Yeah.
Okay. Question in the room before any more virtual?
Is it a good choice for time series?
Repeat.
The
question is it a good choice for time series?
Sorry. The question is it a good choice for a time series? I have not done any time series with it, and I have not seen anybody who has, so I don't want to say that it hasn't been done, but I suspect no. There's Profit, which is like a Bayesian time series modeling that you could look into if you're interested in Bayesian time series models. I think their documentation is pretty good. Yep.
I have a question. So to use the package dbarts or sample dbart, is there any prerequisite packages you need to install?
Yeah. So it can be.
The question is, are there prerequisite?
Are there prerequisite installations for if you want to use dbarts or Stan for BART? So installing dbarts should install a bunch of stuff for you, and if you install it, it should try to install the prereqs for you. You may have challenges with the G Fortran compiler. Now, there's some documentation on GitHub that links you to how to do it. When I've downloaded R, sometimes I've, like when I got a new computer and I downloaded it worked pretty seamlessly. Then there was another time on a different computer where the G Fortran took the whole process. If there are any issues, it's probably the G Fortran compiler, and that I've had more issues with Stan for BART than dbarts, but it will attempt to. I would check the GitHub page, and there's a good description of the installation requirements. Mm-hmm. Yeah. Yeah, one question over there.
You mentioned in the Stan for BART routine that it does an HMC step and then it does an MC step and then all the things. How does that work?
Yeah, so it's all in a big Gibbs sampler. There's basically, it goes back from like a Stan step. So in Stan for BART, whole different talk. That I'm talking about at the DCR conference. And the question was, I'm getting better at this, was, okay, so how can you have this thing where there's like a Stan step and a BART step because Stan's an HMC, and I said BART's a Gibbs sampler, which it is, and so what's going on? So it's all a Gibbs sampler, but in the different steps there's a Stan step where it's modeling the variance and BART's getting the mean. So BART is doing the non-parametric mean, and then Stan is doing the variance conditional on the mean, and then BART's mean is conditional on the variance, and so it's kind of back and forth. It's why it's really slow. There's a whole the Stan part makes it slower, but yeah, it's a cool algorithm, and it's explained in the paper too.
To follow up, does that mean that there's like 4 chains per iteration going back and forth?
Yeah, so there is like I did some, when you do these extract steps, it cleans some things up for you. It's really a 3-dimensional array where it's chains by iterations by people, or individuals, I should say. And so you basically have independent chains that are going, and so you can check chain convergence and things like that. And for Stanford BART in particular, if you're using it, you definitely want to do 10 chains and check the convergence, because there is a parametric piece there too, and so you, yeah.
Then you, do you know if there's a tidy models interface?
I believe there is. Yeah, there is for BART, yeah. You can even pick dbarts as the engine in the tidy models ecosystem.
Oh, that's awesome.
Yeah. So if you're a tidy modeler, there is a, and I checked it actually, and it is there. Yeah. Mm-hmm.
Nice. Cool. Is there a question over there? I see a hand? No. But then
The question was there a tidy models ecosystem?
I'm mic'd at least, so.
Okay.
Yeah, so they can hear me. So I'm trying to be very quiet over here. You talked about tuning over the max depth of a tree, or the depth of a tree. What about actually the number of trees? Is that a tuning thing?
Yeah. So CGM talks about this in the initial paper too. You can tune it too. You can tune the number of trees, and you can use XBART to do it. Like generally, and the number of trees can change the results if you want it to be a little bit more flexible. Adding more trees can make it a little bit flexible, a little bit more flexible. Like if you're, there have been some times in my work where I've explored adding more trees when things weren't going well, but I think generally, and this is a big caveat on generally, tuning the node sensitivity prior, that K prior on the means is the most influential.
Because you're doing a ton of trees anyway, you're doing like 2,000 ultimately, so like.
Well, you're doing 2,000 iterations.
That's true, fair.
Yeah, and again, so CGM talks about it too, that like there's a way where you could make it like fully Bayesian, and the trees would be, like the number of trees would also be calibrated and modeled, but it computationally just becomes too crazy. They pick 200, the dbarts implementation does 75. There have been, like, there's some stuff that like says that like lower is good, some stuff says higher is good. It depends on your use case. Like I said, generally, like there's like the work like CGM showed and other benchmarks have showed that it's pretty good out of the box, but that's another thing you can cross-validate too if you're really trying to maximize performance.
Okay. More questions in the room?
I have one more question. Is there like a summary of the coefficients for each given variable at levels?
So is there a summary of all the coefficients? No, not in like a linear regression sense. In Stanford BART, you can get that, but I would not recommend looking at those coefficients. That'll give you a warning saying not to. We're doing some work right now basically saying like, well, you could add linear terms too, like not as random effects. You could add them as a linear term and then like have that be your baseline mean, and then have the BART part clean up the nonlinear part around that mean, and there may be some computational benefits and some convergence benefits. Some work that's going on now, no definitive answer. But you don't want to look at the coefficients if that's the case, because they're non-identifiable. What you could do though is you can basically look at, and I skipped through it because I was already going way over, but you can, you have your posterior distribution. You can cut it by values of a variable, like I did with country. And that's not a coefficient per se, but it's, you can basically get estimates conditional on. So you can say like, well, the average prediction of this country is this with uncertainty this. So you can do that. Different than a coefficient, and with continuous variables, you can do some binning, and there's some continuous plots you can do too. So you can look at visualizations, but it's not like the traditional coefficient. Yeah.
I think there's another virtual question. Are you going to be? Can you share the code that generated the slides or the walkthrough?
Yes. Yeah. I did it all in sharing again. I'll upload the code, and that's why I had a whole bunch of code snippets too. So if people want to explore it, I encourage you to do so, and you can use the code that I provided here.
Good.
Yeah.
Anyone else in the room before we call it? Nope. Okay. Well, then a big round of applause. Thank you very much for speaking. So just a reminder, we have the R&Gov conference, where you could hear yet a follow-up on this. The third talk in just a few months.
Yeah.
November 14th at NYU, I got an email. There's a bright light. Someone is volunteering to speak, but we need to make sure that works out. And also, we're going to go to the bar. Whoever wants to come, whether you drink or you don't drink, if you come to the bar, you don't have to drink, but come hang out, socialize. We're going to go to the Arts and Crafts bar right around the corner from here. And that is everything. So everyone, please have a good night, and we'll hopefully see you next month. Bye, everybody.